are from Group 10.
We would like to present about one-way ANOVA.
But before that, let us introduce ourselves first. My name is Ikara Sasabila, class student number 033.
My name is Himas Dahlia Indah Juliani. My student ID number is 007.
My name is Alia Konita. My student ID number is 024. Alright, now without further ado, let's get started!
What is one-way ANOVA? One-way ANOVA is used to compare the means of three or more groups. The key factor is that there's only one independent or factor. For example, if we want to see if different teaching methods affect student performance, the teaching method would be the factor. Each type of method is a level. Before we use one-way ANOVA, we have to make sure three assumptions are met. First, the data from each group must be normally distributed. Second, the samples must be independent. And third, the variances in each group must be equal. If these assumptions are not met, the results may not be valid. Let's move to the hypothesis. So in one-way ANOVA, we use two hypotheses. The first one, the null hypothesis or H0 is mu1 equals mu2 equals mu3. It assumes all groups mean are equal. However, the alternative hypothesis for H1 says at least one mean is different. So if we reject H0 or the null hypothesis, it means there's significant difference. But ANOVA doesn't tell us which group is different. Let's talk about partitioning sum of squares. The total variation in data called SST or total sum of squares divided into two parts. The first one SSW or sum of squares within is the variation inside or within each group, and the second part is SSB or sum of squares between is the variation between the group means. So basically SST equals SSW plus SSB. So this is the formula for sum of square within equals the summation from I equals 1 to k of open parenthesis n sub I minus 1 close parenthesis times s sub I squared. So this is the example to calculating the sum of squared within, and the result is 18.35. Then this is the formula, sum of squared between equals the summations from I equals 1 to k if n sub I times open parenthesis x bar sub I minus x bar close parenthesis squared. So as you can see here, this is the example and we already calculated, and the result is 10.86. So this is the formula for total sums of squares equals double summations from I equals 1 to k and j equals 1 to b if open parenthesis x sub ij minus x bar close parenthesis square. And also relationship total sum of squares can be SSE, SSW or sum of square within plus sum of squares between, and the result is 29.21. The variance of the original 18 observations denoted as squared is calculated dividing by the total sum of squares SST by n minus 1, where n is the number of the observations. So a square equals 29.21 divided by 17, which equals 1.72. Determining the calculated F statistic. To test the hypothesis, we calculate F statistic, which is the ratio from MSB to MSW. What is MSB? MSB is the mean squares between groups. Calculated from SSB, the sum of squares between, and MSW is the mean squares within groups. Calculated from SSW, sum of squares within. So if F value is larger enough, so we reject the null hypothesis and conclude that there is a significant difference between the group means. And the next material will be explained by Alia Konita.
Hi everyone, in this video I'll be explaining 3 important parts of one-way ANOVA. First, we'll talk about how to determine the critical F statistic, then I'll show you how to perform one-way ANOVA using Microsoft Excel, and finally, we'll discuss what pairwise comparisons are and how to do them using SPSS. Before we talk about how to do ANOVA in Excel, it's important to understand the concept of the critical F statistic. When we perform one-way ANOVA, we calculate the F value. This F value tells us how much the group means differ from each other compared to the variation inside each group. But on its own, the F value doesn't mean much. To interpret it, we need to compare it with something called the critical F statistic. Think of critical F like a threshold. If our calculated F value is greater than this critical F, it means there's a significant difference somewhere among the groups. To find the critical F, we need 2 values. 1. Degrees of freedom between groups. This is the number of groups minus 1. 2. Degrees of freedom within groups. This is the total number of observations minus the number of the groups. Let's say we're comparing the effects of 3 types of coffee on students' focus levels, and we have 15 participants total. So, degrees of freedom between is 3 minus 1 equals 2, and degrees of freedom within is 15 minus 3 equals 12. Once we have those 2 numbers, we can either use an F distribution table or use Excel's function to find the critical value. Next, let's move on to how to actually do one-way ANOVA using Microsoft Excel. Let's say again that we're testing 3 groups: black coffee, coffee with milk, and decaf coffee. We want to see which group helps improve focus the most. Here's the step-by-step process. Step 1. Organize your data. Put your data into columns, 1 column for each group. For example, Step 2. Run ANOVA. Go to the Data tab and click Data Analysis. Choose ANOVA Single Factor, then click OK. Step 3. Input the data range. Highlight your table as the input range. Make sure to take labels in first row if your first row contains group names, and alpha leave at 0.05 or default. Then choose your output range and click OK. The result should look like this. Step 4. Read the results. Excel will show you a table containing F statistic, the one we calculate, F critical, the threshold we compare it to, and the p-value. If your F statistic is greater than the critical value, or if your p-value is less than 0.05, that means at least one group is significantly different. Now that we've seen how to perform a one-way ANOVA and found that there is a significant difference among the groups, the next question is, which groups are actually different from each other? This is where pairwise comparisons come in. We'll focus on one of the post hoc tests called the Sheffey test. So, what is the Sheffey test? It's a conservative post hoc method used to compare all possible pairs of group means, especially after an ANOVA result tells us that at least one group is significantly different. Shafi is especially useful when you're doing multiple comparisons or when you want to control the type 1 error rate. The formula for the Shafi test looks like this. F sub s equals the square of x bar a minus x bar b divided by SSW over the sum of n sub I minus 1 multiplied by the quantity 1 over NA plus 1 over NB. Let's break that down. X bar A and X bar B are the mean values of the groups we're comparing. SSW stands for the sum of squares within taken from your ANOVA results. NA and NB are the sample sizes of the groups. And sum of n sub I minus 1 represents the total degrees of freedom within the groups. To know whether our calculated F value is large enough to show a significant difference, we compare it to a critical value which we call F sub SC. To get this, we use the formula F sub SC equals open parenthesis K minus 1 close parenthesis times F alpha. For example, if we have 3 groups and our critical F value from the ANOVA table is 3.682, we'll calculate F sub SC equals open parenthesis 3 minus 1 close parenthesis times 3.682, which equals 7.364. If our F sub S value is less than or equal to F sub SC, then there is no significant difference between the groups. But if F sub S is greater than F sub SC, then there is significant difference. Let me give you an example. Imagine we tested the effectiveness of 3 different study methods. Group A, traditional classroom learning. Group B, self-study. And Group C, learning with digital apps. After running a one-way ANOVA, we find a significant result. That means somewhere among the 3 groups, there's a difference, but we don't know exactly where. Well, now, how do we perform the Shafi test in SPSS? 1. Go to Analyze, Compare Means, and One-Way ANOVA. 2. Insert your dependent variable, like test scores, and your factor, like group or method. 3. Click Post Hoc. 4. Choose Shafi, then click OK. 5. In the output, look for the table titled Post Hoc Test. 6. Find the column labeled SIG. That's where the p-values are. It should more or less look like this. If the value is less than 0.05, that means the 2 groups are significantly different. So, in summary, ANOVA tells us if there's a difference. Shafi tells us where the difference is. It's more conservative but very reliable when comparing many groups. Now, I think that's all for my part. On to the next speaker.
Alright, next, let's start to explore one-way ANOVA in SPSS using a real-world dataset about calorie counts in hot dogs. So, our goal here is to see whether the type of hot dog, like beef, poultry, or veggie, has a significant effect on the number of calories. This method helps us to test whether the means across 3 or more independent groups are statistically different. First, let us set up the data. Let's begin by entering the data into SPSS. Now, you can open SPSS and then go to the variable view and then create a variable named calories, like type numeric, and then create another variable named type as string or nominal, and label the groups beef, poultry, and veggie. Now go to the data view. Under the calories column, input the data for all 3 types. Under the type column, input the corresponding label such as beef, poultry, or veggie for each calorie value. Next, let's running the ANOVA. To run the ANOVA, once your data is set, you can click on Analyze. After that, Compare Means, and then you will find one-way ANOVA. And then move calories into the dependent list. After that, move type into the factor box, and then click on options, check descriptive, homogeneity of variance test, and means plot, and then click continue. After that, you can click on Post Hoc and select shift or suitable for unequal group sizes and conservatives, and then click continue and then OK. Alright, next, let's interpret each sections of the output. So here, the descriptive statistics show that the beef group has the highest mean calorie value, M equals 156.00, followed by poultry, M equals 96.00, and veggie, M equals 68.84, with non-overlapping confidence intervals suggesting that significant differences between the groups. However, the Levene test for the homogeneity of variances yields a significant value of 0.018, which is less than 0.05, indicating that the assumptions of equal variances is violated here. And in this ANOVA, or analysis of variance table here, it presents the result of statistical tests used to compare the means of three groups to determine if there are any statistically significant differences among them. The total variation in the data is partitioned into two components, between groups and then within the group or error. The sum of squares between groups is 338.537 with 2 degrees of freedom or df, and then while the sum of squares within the groups or residual or error is 196.361 with 57 df. The total sum of the squares, which reflects the overall variability in the dataset, is 534.898 with 59 total df. Now, to determine whether the group means differ significantly, the mean square is calculated by dividing the sum of squares by the respective degrees of freedom. Now, this results in a mean square between groups of 169.269 and a mean square within groups of 3.445. The F statistic, which is the ratio of these mean squares, equals to 59.059. This large F value suggests a substantial difference in group means. Now, most importantly, the significance value, or sig, is 0.000, which indicates that the probability of observing such an F value under the null hypothesis that all group means are equal is virtually zero. Since this p-value is far below the typical threshold of 0.05, we reject the null hypothesis and conclude that at least one group mean differs significantly from the others. This implies that the independent variable in the analysis has a statistically significant impact on the dependent variable. So that we come to the conclusion. So, in conclusion, one-way ANOVA is a statistical method used to determine whether there are significant differences between the means of three or more independent groups. It assesses the impact of a single factor on a dependent variable by comparing the variances within and between groups. A significant F statistic indicates that at least one group mean differs from the others, necessitating the further post hoc test to identify specific group differences. Now, this technique is widely applicable across various fields, including education, psychology, and then business, and also for analyzing experimental data and making informed decisions.
Thank you for your attention. That's all from us. Wassalamualaikum warahmatullahi wabarakatuh.